Institute in the University of Oxford, and I'm here representing the organisers of the Infectious Dynamics of Pandemics programme at the Isaac Newton Institute in Cambridge. This presentation is part of our workshop on models for the exit strategy. And I'm delighted to introduce our speaker, Marc Lipsitch. Marc is a professor of epidemiology from Harvard University, where he directs the Centre for Communicable Disease Dynamics, which is a centre of excellence funded by the MIDAS programme of NIH. He is also Associate Director of the Interdisciplinary Concentration in Infectious Disease Epidemiology. During this pandemic, Marc and his colleagues have provided excellent novel science, as we shall see today in his presentation. But Marc himself has also provided unique leadership in challenging poor quality science during this pandemic, and has single-handedly made a huge improvement in the communication of science for a range of audiences. And the participants are particularly excited to hear from him because he has a unique experience of challenging that uncertain science in policy in the US. So Marc, thank you very much for your time today, and I'll hand over to you to start your presentation.
Thank you, Deirdre, and it's nice to see a lot of very familiar names, a few unfamiliar on the participants list, so it feels like a bit of a reunion. And thank you all for participating. Let me see if I can share my screen effectively. So my thought was to talk about some of the projects that we've been working on. The first one published, and the remainder of them not published, but in preprint or otherwise. And then I hope have a good discussion. And at the end, I was asked to talk about what we know now about pandemics that we didn't before. That's a big topic, and I'm going to just take a couple of subtopics within that, which I hope are of particular interest to this group. And I'll apologize that this is not the most polished slideshow, but as I said to Deirdre, my standards for presentations have fallen dramatically. And in the couple of talks, I've actually written them while listening to the other speakers in the session. So this was prepared an hour ahead of time. So it's actually much better than my typical. So thank you for your indulgence. As Deirdre said, our Center for Communicable Disease Dynamics has been engaged, as I think almost everyone on the call probably has, since the beginning of February in various activities around this pandemic. So the people whose work I'm going to highlight are shown here in blue and in the pictures, but it's really been a remarkable team effort, and actually really gratifying, for example, to have alumni rejoining us. And actually I see Dan Larimore is another one that's not on here. So it's just been a complete scramble, but with very nice people. I want to start with some work that is published, that was in Science a few weeks ago, about seasonality and social distancing, and then I'll move on to some more recent work. So one of the thoughts we had when this pandemic started was that there are now, in contrast to, say, the time of SARS, and even in contrast a little bit to 2009, there's such a greater infrastructure and capacity in the world, especially in the United States, which was really behind the UK 10 years ago, to do epidemic modeling, that we thought we should try to think of things that were less obvious than some other things, and try to do things that other people wouldn't be doing, because there is, as you're all aware now, really dozens of groups that can do good modeling. So we thought, what would maybe be a contribution that others might not immediately think to do. And so one of the things we thought would be important was to look at seasonality. And of course, actually many others have worked on this. But we stumbled across a data set from CDC that shows the incidence, or proxies for the incidence, of the various 4 seasonal coronaviruses in the United States. These are the 2 beta coronaviruses, and it's not really incidence, it's positive tests per week, either as a number or as a proportion of all tests. And you can see those pretty much overlay on the first 2 of these. We had a lot of discussion about what to use as a proxy for incidence and arrived at an imperfect but okay idea, I think, of using the percent of virus tests positive times the percent of visits in sentinel practices for ILI, influenza-like illness, a proxy similar to one we had used in other work before. There are some issues with it I'm happy to discuss, but that's what we chose to use. And then we used the Mulligatawny approach to estimating the reproduction number, the effective reproduction number from that time series as a proxy for incidence. And you can see it fluctuates, and that it peaks sometime in the fall and troughs sometime roughly 6 months in the spring, and that the incidence lags that by a few months and peaks usually around January or February. And so what we wanted to know was, of course, this annual process is a function of at least two different forces. One is the seasonal variation in transmissibility, and the other is the depletion of susceptibles. And so we tried to separate out those 2 components by using a variant of work from Dennis Tabist and Jaco Wallinga and colleagues, this approach of regressing the effective reproduction number for virus I at week J, or maybe it's virus J at week I, I'm sorry, I'm not positive which of these are, which is, it is, well, doesn't matter. For the reproduction number of each of the 2 viruses in each week as a function of previous cumulative incidence of that virus and the other virus, with the possibility of cross immunity, and then a spline term that's constant across all years, which you can see in the yellow. And what we found was that there is indeed a peak of estimated transmissibility around November or December, and that it's kind of roughly, if you wish to squint, sinusoidal, but certainly periodic in some way. And that then there's also a contribution as incidence of each virus occurs, the susceptibles get depleted, and the reproduction number declines for that reason. And so we apportioned these 2 contributions to the reproduction number, agnostic as to what the mechanism of seasonality is, but just to try to estimate its magnitude. And we found that there was a signal of cross immunity. For example, in this season, there was incidence of both viruses, and this is the blue virus, this is the red virus, and you can see that the red virus depletes susceptibility more than the blue virus, but for the red virus and vice versa. So cross immunity is weaker than same strain immunity, but they both seem to have a signal. And so we then use these as sort of inspiration and partly as inputs to a model that was just a 2-strain SEIR model, which looks like some kind of Tibetan symbol, but is actually just an SEIR model here that Stephen Kissler developed. And to avoid overfitting and keep things relatively simple, we used a sinusoid rather than we fitted a sinusoid rather than the complicated spline, and ultimately found that the amplitude of the fluctuation from peak to trough was about 21%. So that there's about a 21% lower transmissibility at the trough than at the peak. Having fit that model, we can then compare the time series that's predicted to that which is observed for each of the two models with a certain degree of cross immunity. Each of the two strains with a certain degree of cross immunity, and you see a reasonably good agreement in both years, or in both strains. And then we can also go back to the effective Rs that are produced from the purely statistical fit and show that in periods shown with dark dots where there's enough data to really get reliable estimates of the reproduction number, we have a nice agreement. And in periods where there's very much lower incidence in between seasons, there's obviously somewhat more noise, and in fact considerably more noise in the estimates. So from that, we concluded that that 21% was the best fit amplitude of seasonal forcing, and that the rest of the seasonal component was accounted for by the depletion of susceptibles. And given that, and given the sort of historic observation that pandemics are often out of season because they're less constrained by depletion of susceptibles, we concluded that this would not be enough alone. The seasonality averaged over the United States, at least, would not be enough alone to control SARS-CoV-2 in the summer. There are some significant limitations to this, including the fact that the incidence proxy is far from perfect, that we were using national data, and obviously seasonal variation in almost everything varies across a country as large as the US, and we didn't address the mechanism. And I just want to highlight other high quality work that I'm aware of on early evidence of actual seasonality in SARS-CoV-2, which is done by Tama Carlton at the University of Chicago and Mauricio Santillana's group at Boston Children's and Harvard. So then we used those results to try to project what might happen without and then with interventions. And the first thing we looked at was, in the absence of interventions, which is of obviously only counterfactual interest, what used to be called academic interest, now we'll call it counterfactual interest, that the scenarios with the novel coronavirus in black and the red and blue being the other two betas, depending on the extent of cross immunity and the duration of immunity to SARS-CoV-2, you could have phenomena such as annual outbreaks. You could have sporadic outbreaks if there was longer lasting immunity to SARS-CoV-2. If there's permanent immunity, you might have elimination over at least the 4 or 5 year time scale. Obviously, there would be a buildup of susceptibles, and that could change over a longer period, but this is sort of like a post-honeymoon period. If seasonality is more pronounced, then the outbreaks might be more punctuated and larger, but less frequent. And then if there's enough cross immunity, then there's a possibility of a resurgence after several years or a couple of years of not observing the black virus. So then we wanted to look at interventions and their potential effects. And to do this, we used a really extremely simple compartmental model. So, so this is essentially if you had taken the imperial agent-based model and stripped out all the agency and turned it into a standard SEIR model. This is essentially what you would get. And we were quite explicit that there was no reason to reinvent a novel model. We just used this straight SEIR model with 3 possible outcomes of minor illness or asymptomatic hospitalization and critical care. And wanted to ask the question of what would This was in the era when people were saying maybe we can just do one shot of social distancing and that will take care of the epidemic. I don't think many of the people on this call thought that made any sense, but it nonetheless made sense to us to try to model it. So we did, and we considered different periods of social distancing as a one-shot thing. And what you see, fairly unsurprisingly, I suspect to you, is that a short period of social distancing does very little. Black is nothing, and the other colors are up to green are the most intense social distancing. A short period doesn't do much, except that in a scenario where there is seasonality, the short period of social distancing could have pushed the epidemic off into the summer and made it considerably less peaked, and that longer periods of social distancing push it further and then make it potentially either make it worse than it would have been in the particularly troublesome case where it pushes it off into the next winter, a time of higher transmission, or with less effective social distancing, you get two peaks. And as people have found before in the Andreas Handel's paper and other people's work a few years ago, having two peaks is obviously much better than having one because you have less overshoot. And with longer and longer periods, you have variations on those two themes. So if you could really calibrate social distancing, actually a short period plus seasonality, which we don't know about, could make things considerably better, or could make things worse if it's too intense. And then we considered, and I have a slide without seasonality if we want to talk about that later. If you imagine what seems to be happening now, where there's a period of social distancing, and then those interventions are released, and you get resurgence of the virus, then we had this notion of sort of on and off social distancing, which also other people had explored. And mostly what we were interested in was how long would that process take, and how would the intensive care capacity relate to that? Because as you're aware, one of the major goals of trying to slow transmission is to protect the intensive care capacity. So this is the intensive care capacity of beds per 10,000 people in the United States. On a period of on-social distancing, we have the intensive care demands in red and the numbers of total cases in black. So you have a decline and then a rebound when it's taken off, and then a decline. And you can set triggers for such that you protect the intensive care capacity if you can monitor case numbers well enough, which is obviously a real challenge, but possible in principle. Seasonality changes that because it gives you a slower rebound in the summer, and maybe you can accomplish, or you can get more cases accommodated before you get to unusually high loads on intensive care. And then doubling the intensive care capacity allows you to have obviously is good for lots of reasons, but one of the reasons it's good is that it allows you to have longer periods of on and to accumulate herd immunity more quickly, thereby somewhat accelerating the process, especially in the presence of seasonality. And here you see, for example, a very long period because it starts right as the virus is least transmissible under the seasonal assumption, and then as it becomes more transmissible, then you get back into trouble and have to do one more round. So the conclusions are that one-time social distancing wouldn't be enough, and that the impact of social distancing is not monotonic in duration or intensity. If the estimates that we had at the time were correct about the proportion of cases mild versus severe or critical, then several years of intermittent distancing might be required to get to herd immunity without overwhelming the intensive care. And seasonality has a really complicated effect depending on when the interventions are put in place, how much seasonality there is, and other factors, mainly those. So that was work, I should say, by Christine Tedianto, Stephen Kissler, Jonathan Grad, and Ed Goldstein, and me. And that's all passed. And now I want to talk a little bit about some work we've been doing on seroepidemiology, and some of the challenges of that. And this is not all, well, I'm going to talk about the topic as much as about the work we've done, although I'll talk some about the specific work we've done. So as everyone's aware, there's a great interest in doing serosurveys to estimate how close we are to herd immunity. There have been a number of surveys published, mostly on preprints. Okay, a few of them I think are making their way into peer-reviewed publications. And there have been a lot of really interesting lessons we've learned from that already. The first being that there's enormous geographic variation, and down to the neighborhood level. So Chelsea in Massachusetts is a small city right outside of Boston, relatively low socioeconomic status, and the researchers from Massachusetts General Hospital, the biggest hospital in the region, had noticed that an unusually high number of their patients were coming from Chelsea. And so they did a serosurvey in Chelsea, a convenience sample from people on the street, and found that about a third of them, almost a third of them, had antibodies to the virus. And New York had 1 in 5. There have been a number of others. Santa Clara, California had some low single-digit %, depending on what you believe about that study. So some places are very high. New York is geographically quite variable, but high. And other places like Northern California are much lower at the time that they're done. Obviously, this is about a time and a place, not just a place. So this study confirmed that the high disease burden in part reflected high infection burden and not just high rates of complications. All these studies have shown that there's a lot of undetected infection. The Santa Clara study, which led to a lot of criticism and incredibly intense online peer review through Twitter, showed that a little bit of non-specificity, especially when infection rates are low, a little bit of non-specificity, meaning a little bit of false positives, can ruin a study, because when the prevalence is low, the false positives can outnumber the true positives. I think these emphasized the need for expert statistical input, and some of the hazards of overinterpretation. So this whole Santa Clara study is quite a long saga that's fascinating sociology of science and other things, which I won't get into right now, but it has been an interesting side story. So I think one of the lessons of all of this is that we need really truly random samples across multiple jurisdictions to figure out the progress of the epidemic. And apologies for the American bias of this. I think some other countries have much better abilities to get random samples. At least I'm told that the UK does, and I'm told that Spain does. I don't know if you agree with that, but in the US, we've been struggling a little bit to figure out how to get truly random samples of people to test, and then of course they're allowed to say no to having their blood drawn, and so even if you have a random sample, the acceptance rate may be dependent on people's perception of whether they've had it before. So we have various approaches that people are pursuing, and there are of course many targeted questions about individual subpopulations, but it's important to remember that social factors and geography really have huge effects. We need high specificity tests for the reasons that I described to improve the positive predictive value. In other words, the probability that a test positive is actually a true positive. And I'll highlight these sample size calculators in a second. So this is not my work, but work of people in our center and alumni like Dan Larimore. They have put together some nice tools for trying to make sample size calculations and Bayesian interpretation of serosurveys with known sensitivity and specificity or data that inform sensitivity and specificity in a proper Bayesian way. So if people are interested, this is the preprint, and this is the link to the calculators. I've been really trying to push for more social seroepidemiology, and this is the idea that we can learn what the actual mechanisms. We might be able to learn the actual mechanisms by which people get infected by finding out what activities are characteristic of those who have versus don't have infections. So we've seen, especially in the US, where we have a particular talent for poverty, we've seen that poverty and race are associated with bad outcomes and also with infection risk. There's less evidence yet about why. To what extent is it just outcomes versus also the risk of infection? I think the Chelsea study is one indication that it's not just that, it's both. How much is pre-existing medical conditions? How much is the notion that social distancing is a luxury that's easier if you have a bigger house and a job that you can do from home? How much is public transport or the like? As some of you will know, there's a long tradition of what I would call social seroepidemiology for lots of different things, lots of different infections. This is one of my favorites that I use for teaching because it was a PhD dissertation from 1933 in our school, where they looked at household crowding and the age-specific rates of seropositivity for diphtheria. So this is 4 people per room. This is not a wealthy part of the world, rural Alabama in those days. So it's a really good tool, and it has been, I think, used not enough. There's a lot of studying things like zip code or sort of indicators of socioeconomic status, but not the activities that result from that. So this is a call for more of that. And then the last point on serology is this really interesting question of seroprotection, and the question of whether antibody indicates immunity to infection. If so, which antibodies, how much antibodies, et cetera. So we're trying to, the goal is to study this causal relationship between seropositivity and the risk of infection being presumably less via immunity. This is a very hard study to do for a number of reasons. And so as people are setting up these studies, and with Jamie Robbins and Andrea Rutnitsky and others, we've been doing sample size calculations. These studies are going to take, I think, probably tens of thousands of people to get good answers. What are the reasons why it's hard? Well, one reason is that confounding is rampant. So essentially, when you are concerned about confounding in epidemiologic studies, what you're concerned about is common causes of the exposure, in this case being seropositive, and the outcome, in this case infection, which lead to non-causal associations between those two things. But really, you can think of it as the exposure is previous infection and the outcome is infection today. And so essentially you're looking at common causes of the same thing, infection and infection, just at two different times. So there are things like housing density, personal protective equipment, genes, occupation, local incidents, all sorts of things that are common causes of these and will lead to non-causal associations. Another aspect is that we want to study the biological effect of prior infection or seropositivity, but we don't want to be including this whatever behavioral impacts there are. That, for example, if you think you've had prior infection or you know you've had prior infection and you believe that you're seropositive, perhaps you are more likely to expose yourself. And so we also would like to try to exclude this pathway, this causal pathway. And so the challenge is to ensure the comparability of the people who are seropositive and seronegative, so that you have as few common causes as possible, and those people are as close to comparable as possible. I think healthcare worker studies may be optimal for this, but there are other possibilities in different types of studies. So healthcare workers at least maybe have a single typical common exposure. Another aspect that I haven't mentioned, but in recent work, Jamie Robbins and Andrea Rutnitsky have pointed out, is that false positives on serology are really problematic for this as well, because in a population where you have relatively few people who have been infected so far, the seropositives, you're going to have a lot of false seropositives among the tested seropositives, and so you're going to misclassify people and dilute your effect. So this is a pretty challenging study to do, especially in a context where the outbreak is being under control to some extent. So one approach that we've taken to trying to understand this and ways to deal with it is to follow the an approach we followed in the past for other purposes, which is to do simulations of not only of the epidemics, but of the studies in the epidemics, and see how those studies, what those studies conclude, and how they might be misled by factors in their design or analysis, and then how you can improve those studies to account for the epidemic dynamics. This is the report of a meeting we had a few years ago at the University of Washington to explore this, mostly for vaccine trials and sometimes for treatment trials. But in this case, the idea is, can we use simulations of seroprotection studies, so of studies where you follow people who are seronegative and seropositive and see who gets infected, and then compare those rates. So that's what we've done, and so the idea has been to, and I don't want to go into tons of details. There's a manuscript on medRxiv that describes this by oh, I don't have the names here, but Rebecca Kahn is the first author, where we simulate an epidemic and we, so this is the upward slope part of an epidemic. We simulate an epidemic in one or a number of communities. We simulate enrolling people in the trial or in the study to ask whether they have been, whether they get infected, comparing those who are seronegative at baseline to those who are seropositive at baseline. And then we ask the question of whether we get the right answer if we simulate a case where there is no, where there's no protection from being seropositive. Is that what we get back? And so if we have a single community, everyone's enrolled on the same day, on this day, on day 50, and we don't do anything else, then we get the right answer, as you might expect. So if there's no protection, we find that there's no difference between those who are seropositive and those who are seronegative. If we do, on the other hand, a study in which we have multiple days of enrollment, so perhaps people are enrolled on day 50, day 100, and day 150 in one community, and we don't do anything further to adjust, then we get this confounding that biases our estimate in the direction that seropositivity is harmful. And that's because at the early points when people are enrolled, you have fewer people who are seropositives and more people who are seronegatives. And also, the people enrolled here are less likely to get infected on each day after enrollment. This is the height of this bar is the average hazard of infection on each day. And here there are more seropositives because the infection has progressed further. Here there are more seropositives. And in the groups with more seropositives, there are more, you're more likely to get infected each day after enrollment. And so you get this positive relationship that's utterly spurious. It's just due to the timing of enrollment. And you can fix that by matching on day of enrollment, or by stratifying on day of enrollment. And then you can replicate that same problem in multiple communities, because essentially multiple communities are similar to multiple days of enrollment, because the epidemic won't be synchronized in those different communities. And so you have the same problem, and you can solve it again by matching or by stratifying. What you can't completely solve, and I have this on another slide, but didn't put it in this deck. What you can't completely solve is if you assume that there's in fact not a well-mixed model, but in fact that there's some kind of a network and people get exposed to those who they have typical contacts with, because then you effectively get the equivalent of many communities. They're little communities that aren't defined a priori, but just emerge from the epidemic dynamics. They're the communities, they're the sort of local areas within the network. And you get a situation where, to some less pronounced extent, you get a bias that you can't control by stratification or matching, because those communities don't have any existence except in the particular run of the model. They're just places of high or low infection risk. So you can get biases that are hard to control, at least of some magnitude, just due to local effects where individual people's exposure is correlated with their past exposure. Yeah, and this describes some of those problems. And it's related to earlier work that Rebecca led with vaccine trials, and this is really just the sort of equivalent where the exposure instead of a vaccine is seropositivity. So those are two research areas where we're working. I'm finding serology actually one of the most interesting areas and probably where I'm going to put most of my effort, or at least a big chunk of my effort in the next few months. I want to close by a couple of reflections about what we've learned about pandemics from this one, and there are obviously many more things to say. So one is that there are delays and the data quality is a challenge. And so we have infection, symptoms, hospitalization, intensive care, and death. Not everybody goes through each of these steps, fortunately, but these are all things that can happen in the course of infection, and they all have characteristic delays which are changing in time. And the changing in time, this is data that I have not identified. It's just from a place that we've been working with. I didn't get permission to use it, so I'm just going to describe it as data. But these are different weeks of symptom onset. Different weeks of diagnosis and the delay from symptom onset to diagnosis. And you can see it's not all on the same scale. So there are a lot of short delays all the time, but if you compare, for example, this week to this week, you can see there's a much longer tail of delays, and this most recent one, they're actually remarkably long diagnosis delays. So trying to learn those delay distributions is really hard when they're changing week by week, and that's a challenge, which I'll talk about in a second. It's also more fundamentally, in a way, a challenge for control. So this is an analysis that we did from the data in Wuhan, led by Ruoran Li, who just finished her PhD with Megan Murray. And what we found was, and this is just compiling publicly available data, what we found was that in the city of Wuhan, the lockdown occurred on January 23rd, and the demand for critical care or intensive care grew for another 4 weeks. I think this is exactly February 23rd, or plus or minus a day, is the peak demand for, peak need for critical care. And we did this as a comparison against the US capacity as sort of warning about what we would face if this to get to the same point. And I think this graph, in fact, was part of the impetus for some of the shutdowns in the United States that were started early, because it really illustrates that an intervention here has consequences has a lag in its consequences that can be as much as a month. So if you wait until you see the problem to intervene, it's not a good thing. You have this continuing growth because of, actually, it's not entirely clear why such a long delay, but some of it is the delay from when you get infected, which was presumably declining around here, and we'll see that again in a minute, to the time when you need intensive care. One partial solution to the problem of these delays and of trying to figure out how many cases you really have today when you only know how many have been reported is what's known as nowcasting. There's a tradition of this going back about a decade at least. This was an approach that we just published about a month ago or so. It's been languishing at PLOS Computational Biology for a long time, but eventually they decided it was worth making the PDF and putting it online. It was a little frustrating, but because it wasn't about the quality of the paper, it was about delays in getting something online. This is now being used in a number of places. There are also other really good methods, but this is one. And the idea is that the blue here, this is dengue cases from our paper. The blue here is the number of cases initially reported in real time, and the red is the predictions from this model, and the black is what actually turned out to be the totals for that week. And the idea is that essentially this is this is in the initial phases is learning a distribution of delays from onset to report, and then is augmenting the observed cases with those that are predicted to be observed later on in order to make these nowcasts. So it is a useful tool. This is another health department that has been using it to try to figure out the unreported cases as you get close to the present. So that's one approach to the delay problem. The reverse problem, I think, is even harder. And I imagine many of you are working on this and facing it. And I think there are a lot of efforts around the world, some of which we've been sort of hooking up with, but if there are other people doing it, would love to know. So we've been working with James and Rebecca at our school and collaborators at London School and elsewhere. So the problem is, and I'm sorry, I just didn't have time to make a decent slide about this, is that if you have an epidemic curve of cases and you have some delay distribution until you observe them, then you have the observed cases. What you'd like to do is to go from the observed cases, subtract out this delay distribution in some way and get the real epidemic curve. And many of us, including me, would have had the intuition that what you do is to just sample from the delay distribution and subtract from each case, make a set of bootstrap samples, and then you have the original curve. But essentially that's wrong, because you're adding smoothing. The true delay distribution adds smoothing, and then when you subtract that delay distribution, you add more smoothing. So the original curve is a twice smoothed version of itself rather than an unsmoothed version of itself. People have realized this for decades, but it's sort of has to be rediscovered by accident, I think, many times. So in the early HIV era, they developed a bunch of back calculation methods. Optics has this problem of how to unblur images. And so we've been trying to collect best practices about how to do this. And if there are people working on this who would like to join or share, that would be great. Then the last, I guess, on this topic is the challenge of figuring out the reproduction number. And this is a beautiful graphic that Katie Gostick and Sarah Kobe's group created to describe two of the methods that are commonly used, the so-called Corey method that was developed at Imperial, and the Wallinga-Tunis method from our IVM that was developed first. And these take really sort of opposite views of how you estimate the daily reproduction number. The Corey method is a backward-looking method, which looks at people who are becoming observed today and tries to figure out who in the past could have infected them based on the distribution of serial intervals. The Wallinga-Tunis method takes people who are infected today and looks forward to see who they infected and estimates the number that corresponds to that day. And it turns out that this is really important, and I'm sure most people on this, based on the list of people I saw on the participants list, many people are working on this right now. We're all interested in whether the epidemic is growing or shrinking, and which of these methods to use is a challenge. And again, with Sarah Kobe and others, we're trying to do some work on this. I know London School is also trying to do some work on this, and maybe some others. And then retrospectively, there's also the question of, did interventions work? Did they change the reproduction number? And there can be large consequences for small differences in this. I think I'm going to skip this because this is a debate that I'm somewhat passionate about, but I think it will take 3 minutes to explain, and I want to have some time for discussion. So the last thing I want to say is I think there's just, we've discovered that politics and infectious diseases are even more intertwined than we knew. And as an example of this that I found really kind of astonishing, this came from the Atlanta Journal-Constitution, the newspaper in Atlanta. And this is a graph that the Georgia Health Department has been using. It's now no longer there. They have apologized for this graph. It looks like declining cases in the top 5 counties in Georgia. If you look very carefully, and you may not be able to see this on the screen, the dates are 9th of May, 8th of May, 3rd of May, 7th of May, 26th of April, 2nd of May. So this was actually arranged in order of decreasing counts in order to make it look like a decline, when in fact it was relatively flat. And the first date on here is the 28th of April, then the 27th of April, then the 29th. I mean, it's just the most outrageous abuse of data you could imagine. And they blamed it on their software vendor. But this is one example. Another example in the US is that states are beginning to combine results from virus testing and antibody testing so that they have lower % positives and higher numbers of tests. This just came out today, I think, or yesterday. And I can't avoid mentioning also the stalking of Neil Ferguson in this context as another example of politicization of the debate. So I think this is something that's not helpful for any of us, and that could be really detrimental to our field if the models get blamed for outcomes, as I think will be very convenient for politicians and is probably already starting in at least both our countries, if not elsewhere. So on that sad note, I think I will stop and invite some discussion.
Thank you very much, Mark. Yeah, a sobering point to end on, which I'm sure we'll come back to. But thank you also for all of the fantastic science. So we have a few questions which are coming through. We have one from Tom Britton asking about your social distancing study. So could you explain why intermittent social distancing, so if you have social distancing going on and off versus 50% of the population social distancing, can you tell us which is preferable and why you modeled one rather than the other?
50% doing it at each.
Oh, so he says, why consider intermittent social distancing rather than, say, half social distancing the whole time? Is it expected to be favorable for the society, or is it somehow preferable from a preventative point of view?
Well, we considered this because we thought this was what was more likely to play out, which I think in the short term we were correct about. So this was not an endorsement of this as a policy, but rather a description of what its consequences might be. And we tried to be fairly explicit about that. I think the idea of half of part of the society distancing has been considered. A group of economists at MIT has a preprint on this, and I think a number of other groups have been thinking about it. I think what's really challenging about that is to try to figure out the details of what those contacts between and within groups are going to be like. I think past social contact surveys are of limited help because social contacts are completely changing right now. Even in the absence of rules, they're changing, and with rules, they're changing even more. So I think it's, we should think about the consequences of different types of interventions, but I think I'm skeptical about some of the models that have considered those, because I think it's really hard to, for example, the protect the elderly approach in a place with a lot of nursing homes doesn't seem to work even when we're trying to protect everybody. So most of the deaths in some places, and a large fraction of the deaths, almost every place, have been in care homes or nursing homes. And that's at a time when we're doing full social distancing in most such places. So the idea that we could cordon off the elderly with an even more rampaging epidemic going on in the general population seems fanciful to me. On the other hand, you might say, if we can't protect those places even with social distancing, maybe we shouldn't be paying the cost of social distancing. So that's certainly another approach, but I think modeling it is extremely challenging.
Indeed, and it's come up in our workshop actually. How do we measure those dynamic networks in a way that we can actually figure out what's going on? But I shall ask another question for the group. I think this has been during the serology piece. I wonder if household studies allowing for the estimation of secondary attack rates could help controlling for some of the biases you mentioned.
I think they could. I think what would be difficult in household studies is that, especially with relatively small households, the chance of finding somebody who's seropositive, not because of the current infection event, but because of past infection events, and someone who's seronegative in the same household, and an index case who's currently infectious, you start to run out of people. And so you're sort of asking for an exquisite combination of possibly unlikely events. But I'd be certainly excited to hear ideas about ways to do that, because I think households would be potentially one way to do it, if you could solve that problem.
So that somebody has asked you now to elaborate on the backward and forward approach, the Corrie versus Wallinger and Tunis, our estimation approaches.
Sure.
Which I think everybody struggles with. Well, lots of people
Yes,
struggle with. So if you could have another go at that one, we'd appreciate it.
Yes, I'm sorry it was so quick, but the Corrie paper makes the nice point that essentially what her method does is is like a life expectancy at birth, meaning that you obviously don't know, if someone's born in 1900, you don't know that World War I is going to happen and the flu pandemic in 1918. So you don't know that their 18th year is going to be a really risky year for them. What you do know is that in the past, like in some window in the past, the people who are 18 years old mostly didn't die. And so the life expectancy at birth calculated looking backwards from 1900 would say, you know, you might die any of those different years, and there's some probability based on what happened to cohorts of people in the past who were 0 years old, 1 year old, 2 years old, etc. But you obviously can't account for the fact that actually 1918 is going to be a really bad year, because you're not looking forward. And the Corrie method is the best. There are a couple of really good things about it. One is that under its assumptions, it gets exactly the right answer for many things, and we're trying to work with Sarah's group to quantify that. And I know Sebastian Funk, maybe even beyond this, I'm not sure, is also working on that, and maybe we'll join up. I'm not sure. So the one good thing is that it gets the right answer under certain assumptions, and the other good thing about it is that it gets an answer. You don't need to look into the future. It has an answer today for what's today's risk, for what's today's RFT. But it can't get the right answer about today's RFT if the change has been too sudden, because all you know is information about the past. It doesn't use information about the future. And so if people today suddenly can't infect anyone, this method can't know that. On the other hand, the Wallinger-Tunis method can, because it's looking forward at cases. It's saying the number I'm going to estimate today is based on data from the future of today, which means you can't actually estimate it today. You can only estimate it for up to some period in the past, because you don't have, at no time do you have future data. You only have current and past data. So it's always a lag in what you can estimate. And also the other problem with welling of Tunis is that it anticipates, because if something, if this is like 2 weeks ago, and if now future cases go down, some of that's going to be attributed to now, when in fact it should have been attributed to the future. So the welling of Tunis method will tend to predict things too early, and the Corey method can get things too late under certain assumptions. And I'm going to leave it that vague because I don't think I have a completely clear answer. But essentially, because it's looking backwards, it's really good at the past and has some trouble with the future. And because it's looking forwards, it anticipates too much. And maybe just to show this example, this is data from Wuhan published by Pan et al. And grabbed with Data Thief, or one of those digitizers, because they weren't not able to share the data. And 3 approaches to the estimation of RFT, and here is the one line. And so the method they used in their paper was the Corey method. Was the Corey method, and they found that RFT crossed 1 here in first week of February. If you do the welling of Tunis method, you find that RFT crossed 1 in around January 28th or so. And if you lag Corey, which is what's recommended by the Corey paper, by a mean incubation period, then you get that it's somewhere in between, but maybe a little closer to this. So you might say, well, those are all the same shape curves and there's some error, so what's the problem? One problem is that the headline message of this particular paper was, it wasn't until period 4, this time of intense interventions, not just lockdown, but also mandatory out-of-home quarantine, that the epidemic was brought under control, defined as RFT of equals 1. But with other methods of estimation, you put that date, probably with more error than this model seems to suggest, you put that date in period 3, when there was not yet that draconian measure. And a number of proposals, especially in the US, have been made that we need to have mandatory out-of-home quarantine, and very much based on the advocacy of one of the authors of this paper, who happens to be the former chair of biostatistics at our school. And I think that's scientifically questionable, as well as something that I would find a very worrisome thing for the government to try to do. So far, it has not happened, but there are real policy debates that sort of hinge on this kind of very technical question.
Yeah, absolutely. Thank you very much for explaining that. We're actually thinking of doing a workshop on our estimations, so you've inspired me to put a bomb under that one. So we should do that and invite you and your colleagues to that. And I know we've gone over time, so there's been a request for you to explain the back calculation issue, but it depends if you have another 5 minutes or not, or if not, we can skip the final question.
I am supposed to go to another call.
Don't worry. All right. Okay.
But a brief thing to say is essentially, every time you add or subtract a random variable from something, you smooth it. You add blur to it, and so the natural thing. So undoing an addition of a random number is not the same as subtracting a random number. That's the very fundamental thing. The coolest method for deconvolution that I know, because it's relatively understandable, is called Richardson-Lucy. And there's a paper that Ed Goldstein and I did in PNAS about 10 years ago that uses that from 1918 to try to recover the epidemic curve from the death curve. It's probably not the best method. There are 50 years or more of advances since then, but it's a kind of understandable, conceptually clear method, and the Wikipedia page is nice, and there's some nice illustrations online. So I would suggest looking there and to understand the issue, and then going from there.
Thank you. That's really very helpful, Mark. So my last question is, You know, we've got a few more weeks of workshops and no doubt a few more weeks of COVID transmission to go. You know, we've got a real broad team of modelers. I know you guys are working hard, as you said, on the serology, but if you wanted the modeling community to do one thing to clear up any confusion, or what would be the one thing you'd like us to be doing?
Wow.
Or it could be 2 or 3. There's loads of people, so yeah.
Gosh, I don't know. That's too hard a
Don't
question
worry.
for me right now.
Okay, you can email
Right,
it in later.
I'll
don't
email
worry.
you in. Yep.
Yeah, all right. Well, thank you so
Okay.
much for a really interesting and clear presentation, Mark, and thanks to everyone for the questions.
Yeah, thanks everyone. Nice to see
Thank
you
you.
briefly. Okay,
Yeah.
bye-bye.
Cheers. Bye-bye. Bye-bye.